Everybody, please hear. As I remember, we talked about this one also. This one was the last design that we have worked on. So, we talked about truth table, and then we saw that with truth table we can have ones. Okay. 1, you see all of the 1 here, and then if you want to write the function of this, then you just sum the products of the corresponding terms. So this one is, if you want to write a function for this one, it means that only this would be 1 with this input. Hello. Hi. So you see it's not charging here. And so for this we write function. What should we write? When A is 0, B is 1, C is 0, the output is 1. So we can write it as an AND function where the output of the function is 1 at this input, and it would be 0 for all other inputs. So the function would be A naught because it is 0. Thank you very much. B and C naught, and the rest we have seen that before, and we wrote like this. So the function would be 6 terms. 1, 2, 3, 4, 5, 6, 1. 6 products have been summed together. A, these you see. And also we have talked that sometimes it is easier to look at the false positions, because here you see we have only 2 zeros, but we have 6 ones. So maybe it's better to look at the zeros. To do so, we start to look at the negative of the function. The negative of the function would be 1 here and 0 the rest of that. So if you want to use the same method that we had, we can look at these two and write the function of not f1. Here it's called f1, not f1, and we did that. f1 naught is these two, a prime, b prime, c prime plus a prime, b prime, c, with these two. So this is f naught, but f is the not of that. To negate this, we use De Morgan. De Morgan says inverting or would be and. So this plus becomes and. Now inverting of each term. Invert of that, invert of that. Invert of this one, again, De Morgan. Inverting of a product means it becomes or. So this and would become or, and each one is inverted. A prime becomes A, B prime becomes B, C prime becomes C, and this one. Invert of this would be A, B, C prime, and with or. So that would be much easier. It is 2 terms. But A plus B plus C and A plus B plus C prime. But here you can see that the result is a product of sums, not the sum of products. Here in the previous one we had sum of products, but here we went to product of sums. Here we have product of sums. They are the same. They represent the same function, but 2 different representation. And even if you look at this, let me erase all the paintings here. If you look at this, you can make it even more simpler. Any suggestions? A plus B plus C and A plus B plus C prime. Any suggestions? How could we make it more simplified? What? Yeah. Okay, so how do we employ that? B. No, A. No. Oh, you distribute. Exactly, you factor it because you see we have A plus B plus C. We have A plus B plus C prime. So we could use A plus B. So it would become A plus B and dot C plus C prime. Is that right? It is the distributive law. Distributive law says, let's say, for example, A times B plus C is A, and B plus A and C. And it is exactly the same. Here, A plus B is this one, C is this one. Oh, no, we have to use the dual one because here we have plus and then factor it. The same thing. Okay? And it is much easier. You see now, we have A plus B and C plus C prime. C plus C prime is what? Is 1. So 1 and everything would be, so the result would be A plus B. and if you get, if you do more practice and you look at the truth table, you could have guessed it from the beginning. You see the truth table, actually it doesn't, it is not based on C. So the first thing that you could see here, please pay attention everybody. If you look at the truth table, we could see that it doesn't depend on C, because either C is 0 or 1, the result was, then it turned off because the battery was fixed. Yeah, I guess the battery is not good. Let me change that. Okay, this is the multiplexer. As you could see, there is a select input, select pin in the multiplexer, select input. If we put 0 for S, then it means that we want Y to get A, whatever A is. If A is 1, then Y is 1. If A is 0, then Y is 0. And if we put S as 1, then it means that we want B to be the one that makes Y. Y gets B at that time. It's a very good function. Sometimes you need, it is like writing an if in C, for example. In C, you say if this, then do this or do that. This is also the same. Use or like case switch case in C or Java or something. If S is 0, then Y is A. If S is 1, then Y is B. This is the function. Yes.
So it's like conditional gate?
Yeah, somehow you could name it, but in gates we don't have conditional, but you could name it. We call it multiplexer. So it selects one of the inputs. Yes.
Is A always 0 and is B always 1?
No. It depends on whatever A is. It is very good because you select that. A might be 1, might be 0, B might be 1. But depending on S, you say what would be the output of that, either A or B. So let's write the truth table for that. Okay, the truth table. So the truth table has 3 inputs, S, A, and B. And 1 output. So it would be S, A, and B, and the output would be Y. Let's see. If it's good, okay. So let me write all of the functions. All of the states. Oh, 1, 1, 1, 1, 1. 8 from 0 to 7. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. 0 to 7. 8 possible combinations of S, A, and B. As I told you, when S is 0, then Y becomes A. So what would be Y here at the first row? What is A? 0. So Y is 0. What is A? 0. The next row, what is A? 1. What is A? 1. So for this, we just looked at the A. Let me highlight it so you could see that. So for the first 4 rows, we just looked at A because Y gets A. And then S here becomes 1. So when S becomes 1, then the output would be Y, would be B. So here, this is 1. Here B is 0, so the output would be 0. Here B is 1, so the output would be 1. B is 0 here, so the output would be 0. B is 1 here, the output would be 1. Yes?
So like when the S is 0, so the output A.
Yes.
When it is 1, so the output
B, yeah, selects. It is some kind of selecting, switching. It's like a case. Let me just highlight this one also for you. Highlight. How could I make it thicker? Highlight. I don't know. I wanted to make it thicker. Should be somewhere. I don't know. So here is the next 4 rows. Oh, red is bad. Okay. We use this as the output. Yes?
How would the person know which condition to follow on S?
Depending on S.
Yeah, I mean, like if S is 1, how would it know to choose A or B?
So we are going to design that right now. This is exactly what we are going to do. We write the truth table and then we build a design. We design something that it based on S, it selects the output. So this is what we are going to do now. Yes?
So when in the S column, when you have 0 and 1, those correspond, like you see in the diagram.
Which row? 0 to 7. Tell me 0 to 7. Which row?
Just like the S column in general. You see how it's like 0
Okay.
and 1?
Yes.
So that doesn't work. It's not saying like if 0, choose this value, like choose this.
It is like that. Why not? It is like that. When S is 0, then we are using A. But when S is 1, then we are using B as the output. Y gets B. When S is 0, Y is the same as A. And think of this as truth table. We have seen, we have written a truth table. The truth table, this is the truth table. When S is 0, A is 0, B is 0, Y is 0. Okay? When S is 0, A is 0, B is 1, Y is 0. Look at this truth table. So everything is clear here. And then now look at the function of it. If you look at the truth table from the top, you see when S is 0, Y is the same as A. And when S is 1, Y is the same as B. Okay?
But the B value is also, so the first example, the first row.
The first row, okay.
B is also 0.
0, okay. But we don't. But Y gets A at this condition. When S is 0, Y only looks at A. We can say so. But we are going to design it to see how it will be implemented. But for the time being, I say that Y, when S is 0, Y doesn't depend on B. B doesn't have any role in Y when S is 0. And when S is 1, A doesn't have any effect, any role on Y. Okay. This is a very good function. We will use it later, a good gate that you could use in your designs. Any questions? So now what we have done, now we have drawn the truth table. We have written the truth table. Now, like any other circuit, we go to the truth table and select the 1 rows and then write the sum of products. Exactly the same as other designs. So look at the ones. We have 1 here, 1 here, 1 here, 4 ones and 4 zeros. So we will use this one. It becomes 1. This one corresponds to S0, A1, B0. So if I write it, would be S naught plus A, because A is 1, and B naught. So this is the first one. The second one would be A, B, S naught, A, B. S naught, A, B. Okay? Following? Any questions? So this one corresponds to S, A naught, B. S, A naught, B. And this one corresponds to S, A, B. S, A, B. So we have 4 terms, sum of 4 products. 4 products we have, and we are summing them. This is our function. So the function of y is ORing these 4 terms. Okay. So let's simplify it a little. If you look at these 2, S naught A B naught plus S naught A B. So what you could suggest? Could you suggest anything at that time? Yes, you. Yes. Yeah. S naught and A, yeah? S naught and A, yeah? Exactly, you said it correctly. S naught A B naught plus S naught A B. So we factor S naught A. So it would be S naught A and with B naught plus B. Is that right? Agree? Okay. So the next two would be S A naught B, S A B. Any suggestion? You that's fine. Yeah. Any suggestion? Yes. S A naught B plus S A B. What are the common terms here? S, B, and also S. S. So we could factor S, B, and what is remaining? So we have A naught from here plus A from here. Is that right? Okay. Any comments? Okay. So B plus B naught is 1. A plus A naught is 1. So the result would be S naught A plus S B. S naught A plus S B. Okay, let me erase all the inks here and see what I have written before. Okay, S naught A plus S B. And this would be the implementation. Now your question at the end of the row. What was your name?
Oh, sorry.
Musa.
It was answered.
Yeah, so your question would be here. So you see, if you look at this, we could somehow understand it. It says when S is 0, then 0 and with B. So 0 and with anything means 0. It means not, B doesn't have any role because it is ending with 0. So when S is 0, this will be gone and this will be 1, and A is A. So here if you look at this, you see if S is 0, then Y is A. When S is 1, then again the same thing. When S is 1, S naught is 0. So it means that we don't have this, and S is 1, so 1 and B becomes B. When S is 0, we get A. When S is 1, we get B. Okay? So this was another example. I just wanted to show you an example of a design. We wanted to design something which selects between 2 inputs, A and B. And the select would be S. Depending on S, we select A, B, A or B. We could have a 3-input multiplexer. So not 3 input, let me say 4 input because it should be power of 2. We could have 4-input multiplexer, and how many selects do we need? 2, because 2 to the 2 is 4. So depending on S1 and S2, which we select, we either have A or B or C or D as the output. When S1, S2 is 0, 0, then Y is A. When S1, S2 is 0, 1, then Y is B. When S1, S2 is 1, 0, then Y is C. And when both of them are 1, Y is D. So this would be a 4 input multiplexer. We have seen 2 input. You could have 8 input multiplexer with 3 switches, with 3 select bits. So next example, another example. You remember we talked about 2's complement, and we saw how it works when adding two numbers. The numbers could be positive, could be negative, and based on the value of the numbers, they might get overflow. Let's do some examples. Let's say that we have 6-bit signed numbers, 2's complement numbers, 6 bits. So the first example that I will show you is adding 2 positive numbers, which doesn't result in overflow. Give me an example. What do we add so we don't get... when we have 6 bits, we talked about it before. When we have 6 bits, what would be the maximum number, maximum positive number? 2 to the... 2, how much?
255 minus 1.
So it is for 9 bits, 255. We have 6 bits.
127.
127 is for 8 bits.
It's 2 to the 5.
2 to the 5 minus 1. Perfect. So it is 31. 2 to the 5 is 32. Minus 1 is 32. And what would be the least negative number? 32. 32. Minus 32. If you count this number from minus 32 to plus 31, then you would have 64 numbers. That's what should be, because we have 6 bits. 6 bits means 2 to the 6 is 64. We have 64 numbers from minus 32 to plus 31. So this is that we have talked it before. If it is 8-bit, then it would become minus 64 to plus 63. If it is 8-bit, then it becomes minus 128 up to plus 127. Okay. So remember, if I add 2 positive numbers, let's say 20 plus 17, the result would be 37 in decimal. And this is out of the range. So we should get overflow. But for example, if we add 2 numbers, 2 positive numbers, 5 plus 12. 5 plus 12 is 17. So 17 is in the range, so there is no overflow. So remember these 20, let me write it somewhere, so we have to, we want to see what happens when we get overflow. And the same thing that we can say about negative numbers. For example, if you add minus 5 to minus 12, then the result would be minus 17, which is okay. Is it the range? The range was minus 32 to plus 31. But if you add minus, let's say, 20 plus minus 17, then you get minus 37, which is out of range. It means that we have overflow. Okay. Now I want to design a circuit which could say if we have overflow or not. You added 2 things, you got some result, you don't know if there is overflow or not because you just have bits 0 and 1s. Is there overflow or not? For us, we think, okay, 5 plus 12 is 17, so we don't have overflow. 20 plus 17 is 37, so we have overflow. But how could we find out in our circuit, in our design? So let's see. Let me write 5 plus 12. 5 is 4 and 1. So we have 6-bit numbers. 4 and... Oh, what happened? So 5. 5 is this. I just put an example. 5 is not very special number. 5. 4. And 5 plus 12. We want to 5 plus 12. 12 is 8 and 4. Okay. 8 and 4. So this is 12. When we add them, we get 1, 0, 1 plus 1 is 0 and 1 here, 1 plus 1 is 0 and 1 here, 1 and 0. So this would be the result. We expect it to be 17. If you calculate it, it would be 17. 16 plus 1 is 17. Okay. And you see there is no overflow, nothing is here, it's just this number. Let's do now 20 plus 17. 20 is 16 plus 4. 16 plus 4. So this is 20 plus 17. 17 is 16 plus 1. What would be the sum? The sum is 0 plus 1 is 1, 0, 0, 0, 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is 0, and 1 is here, so it's 1. So now you see the problem. We added two numbers, two positive numbers, and then we got a negative number. This is a negative. We have talked about sign. Sign in 2's complement system is the most significant bit. We added two positive numbers, and then the result became negative. And you know why? Because when you think as an unsigned variable, everything is okay, because 20 plus 17 is 37, and here is 37. 32 plus 4 plus 1 is 37. But when we are thinking as a 2's complement, this is not good. So we had overflow. We went out more than 31 here. So remember this one. We added two positive number, and the result has overflow. So now let's do negative numbers. As an example, we calculate minus 5 plus minus 12 as first example, and then minus 20 plus minus 70. So minus 5 plus minus 12. Minus 5 would be, we have to 2's complement it. So this was 5. So 2's complement of that, from the right, come to the first one, and then negate everything. So the 2's complement would be 1, 1, 0, 1, 1, 1. This is minus 5. Okay? You could have calculated it using this one. You negate this one, you complement this one, and then add 1 to it. But it will be easier. You start from the right, look at the first one, keep the first one, and then negate the rest, complement the rest. So this was 12. Yeah, this was 12. So what would be the minus 12? Minus 12 would be 0, 0. We go up to the first one, 0, 0, 1, and then we convert, we negate 0, 1, 1. This is minus 12. So we have minus 5 plus minus 12. So let's add them together. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0 with a 1 here. 1 plus 1 plus 1 is 1 with a 1 here. Okay. We expect this to be minus 17. Minus 17. Do you want to see if it is? Let's 2's complement this. 2's complement this one. Starting from the right, keep the first one, and then negate everything. 0, 0, 0, 1, 0. What is that? This is 17. 16 plus 1, 7. So it was minus 17. We calculated it correctly. We were right. So let me erase this one. Now let's calculate minus 20 plus minus 17. Minus 20. This was 20. This was 20. So minus 20 would be 0, 0, the first one, and then convert everything. 1, 0, 1. This is minus 20 and minus 17. So the first one, and then invert everything. 1, 1, 1, 0, 1. And this one is minus 17. Minus 20 plus minus 17. The result would be 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 0 with a 1 here, 1 plus 1 plus 1 is 0 with a 1 here, 1 plus 0 is 1, 1 plus 1 is 0 with a 1 here. And you see again what happens. We have added two negative numbers. The result became positive. So it means that we have overflow. It is not right. It means that we have overflow. Okay? Now, having said all of these, let's design the circuit. We want to design a circuit when we add two numbers. It could tell us if we have overflow or not. Okay? So let's design the circuit. Remember these four alternatives. Two positive numbers without overflow, two positive numbers with overflow, two negative numbers without overflow, two negative numbers with overflow. So let's see how could we implement that. Let me erase everything. We want something like that. And you know, the result would be based on the sign bit of A and B and the sign bit of the result. We just need that to find out about the overflow. Here, my example here is 8 bits. What I showed you was 6 bits. Doesn't differ. They are the same. It's the same concept. So here we have two 8-bit numbers, B plus A. We have added them together. The sum would be here from S0 to S7. And now we want to find out if we have overflow or not. And here, if I want to complete this as a full adder, in addition to an overflow, we need a carry also here, which we will talk about it later. So that then it becomes a very good adder, a full adder. Two 8 bits added together, we will have a sum, a carry, and an overflow to see how to see the result. So let's see. Let me write now the truth table. Do I have it here? Oh, I don't have it. So I have to write the truth table. The truth table needs A7, B7, and S7 as their input, or in my case, A5, B5, S5. I was 6-bit. Here we have 8-bit. It's the same. So I put S7, which we call it S here. So let me write S. It is easier. S. We have S, we have A. A is the A7, the sign bit of A. We have B, the sign bit of B. And now we want to see what would be the V. V is overflow flag. When we have overflow set, it is set, not reset. It is 1. Okay. I gave you 4 cases. 2 positive number, overflow, without overflow, 2 negative number. So 2 positive number means, okay, let me write all of the 8 possible conditions. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. These are the 8 possible inputs. Now we would like to see what would be overflow. When A and B both are 0 and they are positive. The sign of A and B is 0, so they are positive, and the result is also positive. So it means no overflow. Is that right? Two positive numbers added together, and then the result is no overflow. So the overflow is 0 here. Okay? I didn't give example for you for the other case. One of them is positive, the other is negative. Either A is positive and the other one is negative, or vice versa. Is there any possible of overflow in that case? When one of them is positive, one of them is negative. Overflow never happens. You, for example, let me put a very big positive number. 31 is the biggest one in our 6-bit system. Even if you put the smallest negative number, -1, when you add them together, you get 30. So you don't get overflow. Is that right? When you add a positive number, a negative number, you never get overflow, a positive or negative. Again, the result would be in the range of -32 to +31 in my case, or here from -128 to +127. So when B is negative, A is positive, overflow would be 0 for sure. When A is negative, B is positive, overflow would be 0 for sure. But when A is negative, B is negative, but the sum is positive, it means overflow happened. So here we have overflow. Okay. When A is positive and B is positive, but the result is negative, like 20 plus 17 that I showed you, then it means overflow. When B is negative, A is positive, and S is 1, I don't think it happens at all. So this will never happen. But for sure, it will be 0. I think so. Is it possible that it happened? One of them is 0, the other one. Oh yeah, because the negative might be bigger. For example, you are adding 5 plus -12. So the result would be -7. So it means the result would be negative. So it happens. No, okay, this is but not overflow. One of them is negative, one of them is positive. You add them together, you get a negative result, but with no overflow. It will be in the range. So again, here we will have 0. If A is negative, B is positive, again we get not overflow. If A is negative, B is negative, the result is negative, so it's okay. So it means that we don't have overflow. You see, we built the truth table of overflow detector. And in this truth table, 2 of 8 possible combinations generate 1. It means that we have overflow. When did we have overflow? When 2 positive numbers added and the result is negative, or when 2 negative numbers added and the result is positive. So this is the possible condition of overflow. Okay? So this would be the truth table. Now we could design. Now that we have truth table, so there is only 2, 1 here, so it would be easy. So what is that? S is 0, so S naught. A is 1, B is 1, so S naught AB plus the sum of products. And the other one is here. S is 1, so S. A and B both are 0, so A naught, B naught. So the result would be S naught AB plus S A naught, B naught. This is the design. So this design gives you the overflow. When you have A plus B and you have the sum using A7, B7 as S7 if it is 8-bit. If it is 6-bit, then using A5, B5, S5. If it is 16-bit, using A15, B15, and S15, then you could find out about the overflow. So this is the result. Let me erase.
Sorry, I have a question.
Yes, before erasing.
First
So
row, we have two positive numbers, A and B.
yes,
Why we don't have overflow here?
5 plus 12. What would be the result? 7. Sometimes we have some. When, for example, 20 plus 17. Then this is the case. This is the case. Two positive number gets a negative result. 20. I showed you. I added 20 plus 17 and it became negative. Yes. S is the sign bit of the sum. Yes. Yeah. The result is this, the whole thing. S0 to S7. And 2's complement system, an 8-bit number which is from minus 128 to plus 127. But you should be careful. Sometimes the result has overflow. So it means that you cannot use that result. You have to adjust it somehow. There is overflow. Okay.
So then what is B represent?
Overflow. Overflow flag. We can call it overflow flag. When V is 1, then it flags you, it raises the flag that there is overflow. Be careful. The result is not really the sum of these two numbers. Something is wrong. Okay.
So does that mean that like A and B are to the column immediately right of the signed column?
We have always said that sign bit is the most significant bit. Your question was that? Did I understood correctly?
I'm not sure where
A and B is two numbers. I give you, for example, 5 plus 12. What is 5? 5 is 4. This is 5. So let me write it in 8-bit system so everything would be 8-bit and you don't. 5. 5 is this. 1. This is 5, and since we have 8-bit, so it is 5. Okay. 12. 12 is 8 plus 4. This is 12. When you add them together, then you would get result would be like that. Again, an 8-bit number in 2's complement, the result is positive. This is positive, this is positive, and the result is also positive. It means that there is no overflow. 5 plus 12 is 17. Everything is okay. Everything is normal. But when you add two positive numbers, like 20 plus 17, that was the example in 6-bit. In 8-bit, I can say, for example, 120 plus 100. So the result would be 220, which is overflow, which has overflow, because we have on minus 128 to plus 127, and it is more than 127. It means that we have overflow.
So in the case of like 4 plus 12, like you did there, which one is, or like 5 plus 12?
5 plus 12, yes.
Which one is, like, what does A represent and what does B represent? The fact that they're
An-
positive numbers?
A number, yes, a number. You see, we are designing digital system. Later, for example, it will be used in a computer. Okay. In a computer, you have written a program. In your program, you need to add two numbers. So you have built something which we call it adder, and the adder gets two numbers from you and add them together. This is the design of an adder. if you design and this will be used in computer. In the processor, we have a unit for adding. We call it ALU, if you have heard about it. ALU, arithmetic and logic unit. So it will add two numbers. So how does it add two numbers with this circuit? We have designed it. Now I just designed the overflow flag. Later we will design the sum also. How do we add these two numbers together and get the result? I haven't talked about it here. I just showed you the overflow detector as an example of a design. Later we will talk about the full adder. So how could we calculate the result? So your question, if I understood correctly, was where is A, where is B, where did they come from? So they come from your request. You are using these things. You are building something to add two things. You are building something to calculate so many things. So these are your inputs.
So here I have two inputs and also I have two results. I have four inputs.
For what?
Four inputs.
For inputs. No, we have actually two inputs, A and B.
If we have four, I also will have
For adding, oh, you have to do it 2 by 2. So you add two of them together. If you got overflow, then that's it. And if no, we go to this next one. So if you got overflow, then no. Because overflow is accumulating. If you have overflow somewhere, that it means that they told that the last time. Unless one of them is positive, one of them is negative, we could talk about it. Yes, there was a question there, no? Okay. So this is the result, and if you want to show it as a circuit with logic gates, it would be that. You see A, B, and S naught, and A naught, B naught, and S, and then they are ORed together. So this is the same as we have it here. This is the result, and this is the implementation. Okay. Oh, let me, so because it's almost, we are at the end of time, so maybe it's good to have this, also I tell you this. Here you see, let me erase this, you see it correct, it's a good thing. Here I have designed a circuit. Is it okay? A naught, B naught, S plus S naught, A, B. This is using primitive gates for designing that. So everything is okay. But if you remember, I told you about NAND, which would be better for implementing. Each NAND gate has two-input NAND gate has 4 transistors, and every two-input AND gate has 6 transistors inside. So it means that it takes more space, and is taking more space than NAND, and also has more delays because it has more gates, it has more delays. So it is a good idea if we could convert our circuit to something using only NAND. Here, as an example, I show you something which is just by intuition, just ad hoc, just look at them, but we will talk about this maybe later. Okay, let's see what happened here. This is an AND gate. Okay, I am going to change it to NAND because I told you NAND is better. If I change it to NAND, then it means that I have a new function. Here we have something as output. Here we have the NOT of that. They are not the same. What should I do? I should put a NOT here so they will be the same. I inverted here, so I put another inverter here. So they are not the same. Okay? Okay? Do you agree? Okay? One invert here, one invert here, and one invert here. So that would be the same. Now, this invert, I put it here as the input of my OR gate. And this, I put it here as the input of OR gate. So now what do I have? I have 2 NAND gates here and a gate like this, a NOR gate with 2 knotted inputs. What is this? What is this? No. Or no. Because or, if it was or, we have to put an inverter here, then it will become NOR. So we have 2 inputs, NOR and then that. Yes. Why? Why? Okay. So how could you reach the NAND gate? Because you know that I want to reach the NAND gate. Yeah. You're right. We have De Morgan. De Morgan. So let's do De Morgan. So this is the De Morgan. De Morgan of 2 knotted inputs. When you have A naught plus B naught, and they are knotted all at the, because this is the knot is here. So let's do De Morgan. De Morgan says you use A and B, and then that's it. And then we have also this at the output. You remember why we had this? Oh, we have to do this because we put a knot here, so we have to. So this will become an and this is a knot. This AND plus this knot is what? NAND. So we change this to this. Very, very good. Instead of having 2 3 input AND plus 1 2 input OR, now we have 2 3 input NAND plus 1 NAND. 1 2. This is NAND. This is NAND. You know, this is NAND. Exactly as you told us. Very good. So this was just a fun thing that I wanted to show you, that we could somehow change this to this, and it would be much easier, much better design, has less transistors. In the next session, I will count for you the number of transistors for these 2 designs. So what we told you, we talked about Boolean algebra, theorems, and gates, and then realization, and then obtaining the result, the function from truth table. Thank you very much. Have a good time.